Welcome to this class. Let us continue from the last class. In the last class, we have discussed regarding the prepositions, how prepositions will be an important role in order to construct some statement or assertion, and that statement can have the judgment or can have the opinion. That assertion which you are doing it, that statement may be true, may be false. Okay, and we have seen the simple propositions how it is, and from the simple propositions how can we make a compound propositions. The compound propositions can we make it using 5 logical connectives that we have seen, that is disjunction, conjunction, negation, equivalence and implication. Disjunction is as good as your maximum operator, conjunction is your minimum operator, negation your complement, implication and equivalence, these are the two maybe new for you, and we have seen what is implication, what is that, and how can we compute it. So for example, if I am saying P implies Q, so this implication may be of two types. One may be P entails Q, or second may be P coupled with Q. Okay, and this can be computed using P bar union Q, and P coupled with Q can be computed using P intersection with Q. So we'll see this when again in details. We need such kind of operation to design the controller. We have also seen the couple of examples related with each operation or each logical connective. Also, we have seen the tautologies. What is the meaning of tautology? What is the meaning of contradiction? So, tautology is that where the statement or the compound statement will always be true irrespective of the simple propositions. Then if this is the case, then that kind of thing is called tautology. Whereas in contradiction, the resultant will always be false, even though whatever may be the simple propositions that we would have been used to compute or to form the compound assertion or compound statement, we can say. Okay, and we know modus ponens and modus tollens, we have proved it also. Now next, what we will have some hypothesis we'll be writing in statements, and let us try to express it into symbolic form, and that all we are dealing with the crisp set of theory. Once we are familiar with this crisp set of theory, that how to express all the proposition, then we'll switch on to the fuzziest kind of representation. Okay, so here I have written some statements. For example, first statement is this is the hypothesis that engineers are mathematicians. Second hypothesis is that logical thinkers do not believe in magic. And third statement is that mathematicians are logical. And what is the conclusion? Conclusion is that engineers do not believe in magic. Now this all I have to write it into symbolic form. So in order to do that, let us define the proposition first. So P, let me call is one proposition, and this is defined as a person is an engineer. Q is suppose is a mathematician. R is the person who is believe in magic, and S is the person who is a logical thinker. Now let us write using this symbols the hypothesis which we made it. So first is engineers are mathematicians, and this is the implication. So engineers are mathematician means if it is a person is engineer, it implies that it is a mathematician. So P implies Q will be the one symbolic form. Then second statement means it is the conjunction, so I'll do conjunction. Then we'll say that logical thinkers do not believe in magic. So logical thinkers is represented by symbol S, and it implies that it doesn't believe in magic, so it implies that it is R bar means complement. Then next is the conjunction with mathematician or logical. So mathematician is represented by symbol Q here, and Q implies logical. So Q implies S. Okay. And from this, what is the resultant? The conclusion is that engineers do not believe in magic. So it implies that engineers represented by symbol P and do not believe in magic. So P implies R bar. This is the way you can write it. And what is the truthness? You know how can we find it out. Okay. And the truthness will be generally used to indicate in terms of zeros and one. Suppose now second proposition I'll write. Let's say this is the example with the contradiction. So suppose example 2, let us have the hypothesis that if an arc dam fails, the failure is due to poor subgrade. This is one statement, and second statement is an arc dam fails. So what is the conclusion? Conclusion is that arc dam failed because of poor subgrade. So let us form the composition. So first let me write P is the symbol which will be represented as arc dam fail. Okay, then Q is the symbol I will write, and which is defined as arc dam fails. This first statement, arc dam fails, this is because of or due to poor subgrade. Okay. Now let us define the overall example 2 in symbolic form. So what we can write here is that is first is an arc dam fails, and second is if an arc dam fails, the failure is due to poor subgrade. So P and arc dam fails, it implies because of the poor subgrade. P implies Q, and again an arc dam fails, so conjunction with arc dam fails, so this is in conjunction with P, and this implies that what is the conclusion? Arc dam failed because of poor subgrade, and that will be represented using Q. So this is the example for the contradiction. Now let us think, is it tautology? And what is tautology? The statement is always true irrespective of the simple propositions or simple compound simple statement. So this also can be proved using the contradiction, and we know how to say the contradiction. For example, if I am saying P implies Q as a tautology, how can we say that? P bar can be computed as P bar union Q, and in terms of contradiction, if I would like to say, so it will be P intersection with Q bar. Okay, so I can use something to prove as a tautology in terms of contradiction, or contradiction I can prove in using by taking the help of tautology. Okay, so let us this is a tautology or not, if that I would like to check it out. So that can also be proved using the contradiction, and let us see how can we write this. Okay, so let us prove by contradiction. So suppose this is my statement, P implies Q conjunction with P, and this implies Q. So using contradiction, what can be written? P implies Q, then it will be conjunction with P, and instead of or it will be and it will be the complement of resultant, that is false, Q bar. Okay, and let us solve this now. P implies Q, how can we write now? P bar union Q, we know, and P again conjunction with Q bar. Okay, so this is what the representation I have converted into the contradiction form. Okay, and now I have to solve it. So this P implies Q can be written as P bar union Q conjunction with P conjunction with Q bar. Okay, and as we already know, as already we discussed, if P implies Q, that can be written as P bar or Q, and in terms of contradiction, P and Q bar. This is what we made it. This is the resultant. Okay, and from that it implies Q. So this will be as it is, and ending with the Q bar of it. Okay, then I don't have to change here because contradiction already I have done it. Okay, now here simply I have to follow the rule, that is P implies Q can be written as P bar union Q and P and Q bar. Now let us check it out whether resultant will be false for the combine or so many combination of statements. So let us take the help of truth table. So suppose P Q, let me calculate P bar also, Q bar also. Then what I need to calculate P bar union Q. That I have to calculate P bar union Q with ending P. Then P bar union Q and P and Q bar. Okay. So what are the possible statement that we can make it? Either P 0 0, this may be 0 1, this may be 1 0, and this may be 1 1. Okay, now what will be P bar? So this will be P bar will be 1 1 0 0. What will be Q bar? It will be 1 0 1 0. Then find out P bar union Q. So this will be maximum, so it will be 1 1 0 1. Then find out the minimum operator, that is P bar union Q with ending P. So it will be 0, this will be 0, this will be 0, and this will be, I'm sorry, so yeah, this will be 1. Okay, and then add with the Q bar. So this is ending with this Q bar. So what is the result? It will be 0 0, this is 0, and this is 0. So you can say here the contradiction, the compound thing will be always false irrespective of the simple propositions, whether they are true or false, I won't matter, but resultant has to be always false, means it is having the tautology. Okay, so this is the way to check it out for the tautology or in order to take some decision. Okay, now next we will again say we will see the details in implication. So implications are also called the deductive inference. And what is the deductive inference? So deductive inference is also obtained from the implication, and deductive inference is that we know the implication generally in two different universal sets. So as we have already stated that if I made a statement, if A then B. Okay, so how can we obtain the relation in the form of product space? Okay, so this can be obtained the relation as R will be equal to if A then B. So that is A coupled with B, and what if not A, then what? That I have to complete the sentence. Okay, if A then B, very good, but if not A, then what to do? So if not, then take it the complement, and this will be coupled with the next universal with the universal set as overall Y. Okay, if C is not given or if anything is not given. Okay, again let me change the way of my statement. If I am saying if A then B else, then let me see B else C. Now in this case I am properly giving that if A then B, if not A then what? Then C, and from that I can write as a relation matrix in product space can be obtained as A coupled with B, that is A cross B, or if not A means A bar coupled with C. Okay, so that way we can do the inference. Okay, let us take the example that how to obtain the relation matrix. So for example, suppose I have some system and where I have two variables, for example temperature and pressure, and that let me say the temperature is represented as the universal set X. Okay, and say universal set y represented as the variable, suppose pressure, and suppose the numbers, these are 1 2 3 4, let's say these are the numbers represented for temperature set, and say pressure, the numbers are represented as 1 2 3 4 5 and 6. Now next what we'll do, we have to evaluate the two sets, for example. So for that, let me make it the two sets, that is A is one set from this universal set x temperature. So let us say A is 2 comma 3, and suppose I make it, I will do others, I will form other set, that is B, and suppose it is 3 comma 4. Okay, so with this now, let us express it into the set theory form. So suppose x will be what, x will be 1. Okay, 2 is also 1 because the membership is always 1. For 3 is 1, and for 4 is also 1, because in crisp set the membership used to be represented with either 1 or 0. Okay, so based on it, what will be the representation of the membership for A in crisp set? It for 1, there is no membership. For 2, yes, it is 1. 3, yes, it is there. 2 is there, 3 is there, but 4 is not there, so it is absent, means represented with 0. Similarly, let us represent for B also. So for B is 3 4, so for 1 not present, 2 not present, 3 yes, membership is there, 1, 4 membership is there, 5 not present, means 0, 6 also not present, means 0, because universal set has been expressed from 1 to 6. That's why I am representing the set B from 1 to 6, and in set B what are the elements present? 3 and 4. Okay, fine. Now let us obtain the relation matrix here. So to obtain it, what to do? If A, then B, else C. First let us see, let us obtain the R, or the relation matrix for rule 1, that is if A then B, that's it only. Okay, so for that what can be written? Relation matrix can be written like this, where A coupled with B or A bar coupled with Y. So let us obtain first A cross B. So A cross B is nothing but your max operator. So A is what? A is recently we have obtained, that is 0 1 1 0. So let us write 0 1 1 0. What is B? B is this one, that is 0 0 1 1 0 0. Okay, so find out what is the resultant. It is 4 cross 1 is 1 cross 6, so resultant will be 4 cross 6. So it will be 0 0. What is the minimum? 0 0 0. What is the minimum? 0 0. Just do the matrix multiplication sort of it. Okay, 0 0 minimum is 0, 0 0 minimum is 0, 0 1 minimum is 0, 0 1 minimum is 0, 0 0 minimum is 0, 0 0 minimum is 0. Okay, so all will be 0. Now take it the next element from this row and do for all columns. So it will be again for the first two 0 0, then 1 1 0 0. What will be for third? It will be again 0 0 1 1 0 0. What about fourth? Again same, it will be 0 0 0 0. This will be 0 and 0. So this will be the resultant A cross B. Now let us obtain A bar coupled with Y. Okay, so A already we know, that is 0 1 1 0. So now let me obtain A bar coupled with Y. So now A bar will be 1 0 0 1, and what will be Y? Y will be the presence of all the all the elements. It means it will be 1 1. How many times? 6 times. 1 3 4 5 6, because the universal set has been given as element 6. So now let us compute. It will be 1 1 1 1 1 1 1. Then take it the minimum from this, that is second element, and all the columns. So it will be 0 0 0 0. This is 0, this is also 0. Similarly, this is 0 0 0 0 0 0. This is also 1 1 1 1 1, and this is 1. Okay. Now what is to be done? I have to, this is suppose R2, let me name it, and this is R1. And what is to be done as a relation matrix to obtain A cross B? If A, then B, and or if not A, then what? Then your Y. Okay, if something is not given. Okay, so now what I have to do? I have to obtain the union, that is, let me write R, and this is simply the union operator. So union operator means max, so take it the max from here to here, that is 1. This is 1. Element to element, this is 1. Okay, from first row this is 1, this is 1, this is also 1. From second row 0 0 1 1 0 0. So resultant, let me write what will be first row. It will be 1 1 1 1 1 1. Next will be 0 0, then 1 1, then next 0 0. Next will be 0 0 1 1 0 0. The next will be 1 1 1 1 1 1. So this is the resultant R matrix. Okay, these are all in classical set theory. Okay, now if I would like to calculate for C, that is, if the rule is given that if A, then B, else C, then C should be given, and once C will be given, then you can calculate relation matrix as it will be like A coupled with B or A bar coupled with C, and the procedure will be same to obtain the relation matrix as recently we have seen. Okay. Now next, this all what we have seen along crisp theory or classical set theory. Now the same thing, basically our aim is to see in fuzzy logic. So let us see all the representation in terms of fuzzy domain. Okay, so prepositions, let us say this is my truthness of preposition and represented as U as an element which is in universal set capital U, and what will be the range? It will be in 0 to 1. Okay. When the truthness will be 0, means it is fully false. Okay, and if truthness is 1, means it is fully true. Okay, these are generally used in classical theory. But what about the situation where I cannot tell something is fully false or fully true? So this kind of representation can be evaluated by the use of fuzzy logic. Okay, so in fuzzy logic, what I have to do? I have to define partially true or partially false kind of situation. Okay, so truthness of P is defined. Let's say now here I will not use P as fuzzy representation, so let me use P bar. Okay, so truthness of this P bar will be partially true or partially false, mean, which will be between 0 to 1. And for that, the same formulas, the same thing can be adopted, except instead of 0 or 1, what we have to use? We have to use the membership values. That's it. And again, same logical 5 connectives, that is the disjunction, then conjunction, negation, same, then your implication, and this will be helpful for me to define the rule based system. So what will be the disjunction for the fuzzy representation? So let us define disjunction for fuzzy representation. So suppose disjunction is to be represented with symbol this. So truthness of this p bar disjunction with q bar, that can be represented as, it is the disjunction, so it is the max operator, so it is maximum from truthness of p bar and truthness of q bar. Okay, where this belongs to set A, this belongs to fuzzy set B. We know that. Okay. Then for conjunction, this will be represented as symbol this. So truthness of this for two propositions, two connectives, can be obtained using the minimum operator, and it will be minimum of truthness of P and truthness of Q. Here it will not be 0 and 1 like what we did for classical set theory, but it will be between 0 to 1. Okay. Third will be negation, and negation is simply to obtained as a complement. So truthness of P complement can be obtained 1 minus truthness of P bar. Okay. Then implication also same, but only the change with the membership. So truthness of P bar implies Q bar can be obtained as truthness of P bar complement or Q bar. Okay, and this how to obtain? It can be obtained using max operator, which is max of truthness of P bar complement with truthness of Q bar. Okay, so this way you can do the logical connectives, and this will be useful to form the rules. Okay, so let us see the rule based system. So for that, if suppose I am saying if some variable x is a bar, then next universal set, next element from universal set y is b bar. And how to find out the relation from it? It is same, that is relation, let me represent r bar, which don't denote the fuzzy representation. This can be defined as a bar coupled with b bar. If not, then what next? A bar complement coupled with y. Okay, so this is the coupled, a bar coupled with b, and a bar union b is a entails b. That way we can define it. Okay, now if I am saying, let's say, if next rule, if x is a bar, then y is b bar, else c bar, and where a bar belongs to universal set x, b bar belongs to universal set y, similarly c bar belongs to universal set y. Okay. Now let us find out the r bar in terms of fuzzy domain with some specific example. So let me take the two universal sets. One universal set is x, which is represented as, for example, 1, 2, 3 and 4, some variables. Okay. Similarly, the next universal set let me represented as 1, 2, 3, 4, 5 and 6. And from that, let me define one fuzzy set a bar, which is, for example, membership function 0.642. For 3 the membership is 1, for 4 the membership is 0.2. Okay, and similarly define b bar, which is, suppose for 2 it is 0.4, for 3 it is 1, for 4 it is 0.8, for 5 it is, for example, 0.3. Okay. And let me give you the c bar also. So suppose it is 1, the membership is 0.3, for 2 membership is 0.5, For 3 membership is 0.6. Similarly for 4 say membership is 0.6, 5 membership is say 0.5, and for 6 say membership is 0.3. Now let us calculate if A bar and then B bar, only for that. If this is the rule, then how to obtain the relation matrix. Okay. So in order to have the compatibility, we just have the universal set A bar compatibility with the processing. So let me make it this A bar order of 4. So for 1 it is 0, for 2 it is 0.6, for 3 it is 1, and for 4 it is 0.2. Okay. Similarly, let me make it B bar length is equal to the length of the universal set. For 1 it is 0, for 2 it is 0.4, for 3 it is 1, for 4 it is 0.8, for 5 it is 0.3, and for 6 it is 0. Now I am using only the rule as if A bar then B bar. Okay. If this is the case, then how to obtain the relation matrix? It will be defined as R bar is equal to A bar coupled with B bar, and not A bar, then what? Then it will be A bar complement with universal set Y. So first find out A bar coupled with B, and then find out A bar coupled with this Y. Okay. So first let me find out A bar coupled with B bar, and this can be defined as what is A bar. Say for example it is 0.6, 1.2. Okay. And what is B bar? B bar is this, which is 0.4, 1.8, 0.3, and 0. Okay. So from that we have to use A cross B means minimum operator. So 0 into 0 just simply as of matrix multiplication. So multiply this row with all the columns and select the minimum. So it is 0, then this is also 0, third 0, 0, 0, 0. From second row with all columns, so 0.6 with 0, minimum is 0, 0.6 and 0.4, minimum is 0.4, 0.6 and 1, minimum is 0.6, 0.68, minimum is 0.6, 0.3, minimum is 0.3, and 0.60, it is 0. Similarly for third column, it will be 0, 0.4, 1, 0.8, 0.3, 0. Fourth row, it is 0, obviously, 0.2, 0.2, then 0.2, again this will be 0.2, and this is 0. Okay. This will be obtained from A bar coupled with B bar. Now next obtain A bar complement with Y. So Y membership will be all 1. So let me write now A bar complement with Y. So A bar is now 0.61.2, so complement will be 1.4, that is 1 minus 0.6, 1 minus 1 it is 0, 1 minus 0.2 it is 0.8, and Y will be the presence of everything, so it will be 1, 1, 1, 1, 1, 1, 6 times. Okay. And resultant will be the minimum operator, so it is 1 for first row, so 3, 4, 5, 6. Then next is 0.4, so 0.4 will be same, so 0.4, 0.4, 0.4, 0.4, 0.4. Next third column will be all zeros, fourth column will be all 0.8, 0.8, this is 0.8, this is 0.8, this is 0.8 as well, this is 0.8. Okay. And now what is the resultant? The resultant is I have to obtain the relation matrix R bar, which will be defined as A bar coupled with B, or if not, then A bar complement coupled with Y. Means what? I have to find out now the union operator or the disjunction operator on, let me write, this is R1 bar and this is R2 bar. Okay, so what will be the resultant? Suppose, let me write here. So it is the max operator, so first row will be all 1. So 1, 1, 1, 1, 1, 1. Next is max operator means 0, 0.4, so it is 0.4, 0.4, then max is 0.6. Let us compare the second row from R1, not compare means let us check it out, the second row from R1 bar and second row from R2 bar. So it is 0.4 is max, 0.4 here max, 0.6 is max, then 0.6, 0.4 and 0.6. From third row, what it will be, third row here it is 0, so obviously this third row will be as it is, it will be 0, 0.4, 1, 0.8, 0.3 and 0. From fourth it will be max is 0.8, this is 0.8, this is 0.8, all 0.8, 0.8 and 0.8. Okay, so this way you can obtain the relation matrix which will represent the rule. What is that rule? If A bar then Y bar, if A bar then B. Okay, and now if C is given, means if A bar then B, else C bar, then instead of Y, what would have been happened? It would have been C. Okay, so now this relation matrix will be helpful for the event which will be changing from A bar to A bar dash, and once I know A bar dash, you will be able to calculate B bar dash. Let's see how. Okay, so that is represented using approximate reasoning. Now let us look at this, what is approximate reasoning and why it is called as approximate reasoning. Basically, approximate reasoning means which will be neither the fully precise or nor imprecise. So you will be able to know why it is called as approximate reasoning, because generally whatever the relation matrix we have been obtained, okay, which has been obtained from two things, that is A bar and B bar, we obtained some relation matrix R bar. Okay, now if I would like to obtain the B bar from A bar and R bar, if B bar will be same as of already which has been computed from given B bar, then okay, then there will be reasoning. But if B bar, what resultant we are obtaining, will not be same as of given, then that is the approximate reasoning. What I meant to say, generally till now what we said, we know A bar and B bar, and we have obtained R bar as a map function. Okay, now what is to be done? Now R bar I know it, A bar I know it, okay, and I should be able to obtain B bar. Okay, so this B bar can be obtained basically using the composition, so that can be written as A bar composition R bar. And what should be my possible B bar? B bar should be as of the same from which R bar has been calculated. But we observe in fuzzy theory that B bar will not be same, whereas in crisp it will be same. That we'll take it with the example. So first let us check it, let us see with the rules how to obtain. Okay, to go into this computation, let us start with first let me define the two rules. For example, rule 1 is saying that if X is A bar, then I am saying Y is B bar, and these rules are generally used to design the system, maybe the fuzzy logic controller or maybe any expert system. Now if I am saying if X is A bar dash, then Y will be B bar dash. Okay, so what is to be done? X is A bar, B bar is given. Now if X is A bar dash, then what will be B bar dash? This B bar dash I have to obtain it. How? That is what we have to do it here. Okay, so how to do that? In order to do that, first let us form the rule. Let us solve for rule 1, which is given that x is a bar, then y is b bar. So for that, relation matrix can be defined as a bar coupled with b bar, or a bar complement coupled with y. Now I know r bar. Now this r bar will be helpful for me to obtain b bar dash, this b bar dash. Okay, and this b bar dash can be obtained using composition operator, and this b bar dash can be written using composition operator as, because a bar dash has been changed from a bar to here. Now what will be my corresponding change? Okay, so for example, this is my antecedent, this will be my consequence. Okay, so if there is a change in the antecedent means input. So if there is a change in input, then what will be the corresponding change in input? That basically I have to compute it. So first, with the rule 1, I have defined, or I have obtained the r bar. Now that r bar I will use to compute the consequence from second antecedent, and this can be done in fuzzy theory using composition. So b bar dash can be computed as a bar dash composition operator with the relation matrix which has been obtained as r bar. Okay, and basically if whatever we have done, this is called as reasoning. Okay, and why approximate and all that will come to know. Okay, so this is basically reasoning. What is that reasoning? Once I know the relation between two fuzzy sets, and if there is a change in one of the fuzzy set, what will be corresponding? I mean, if there are the changes in two rules, or one rule is like this, then if I would like to obtain what is the corresponding change in that, or what is the corresponding change for that particular antecedent, I should be able to compute it, and that can be computed using reasoning. Okay. How will it be? This will be like, suppose I have universal set x, I have universal set y, and from the two universal sets with a bar and b bar I obtained this relation matrix like this. Okay, suppose something like r bar. Okay, and this was something a bar and b bar like this. Now this a bar, that is this antecedent, has been changed here, a bar dash. Now correspondingly I have to obtain what will be my corresponding b bar dash. So what to do? You take the projection. Okay, I have taken the projection and project on y. So what will be the projection? Projection will be this. So this will be my b bar dash. So what is the procedure here? First I am extending this line interval here, and then I am taking the intersection. Means what? I am finding out the minimum, and then I am finding out the maximum. Okay, means it is what your max mean as good as same. Okay, so this whatever the procedure we have seen graphically, this will be your max over x, and this is minimum, a bar dash with your r bar. Okay. So that's why the composition operator will be helpful to do the reasoning in fuzzy set theory. Okay, so let us continue this. Let us see with example. So the same example which we have seen recently, that was the computation of r. This we will take it as it is, a bar b bar same, and let us find out what will be my b bar dash. Okay, so let me rewrite the relation matrix which has been obtained recently. So r bar was 1 1 1 1 1 1, then next row was 0.4 0.4, then this was 0.6 0.6 0.4 0.4, then third row was 0 0.4 1 0.8, then this was 0.3, this was 0, then fourth row was all 8 0.8 0.8 0.8 0.8, and this is also 0.8. Okay, and now I would like to calculate b bar dash. So for that there is a change in the consequent. So suppose my a bar dash is like this. 1 it is 0.5, for 2 the membership function is 1, for 3 the membership function is for example 0.3, and for 4 suppose it is 0. Okay, and now from that I have to find out what is my b bar dash. Okay, so what is given? A bar dash is given, b bar dash is given. If a then b, this has been computed using r bar. Now instead of a bar, suppose there is a change in antecedent a bar dash, then correspondingly what is the change in its consequence that I would like to obtain, and that can be obtained using composition operator, that is a bar dash composition with your r bar. Okay, and here also we will use the same matrix multiplication sort of it. So b bar dash will be a bar dash is 0.5, 1, 0.3 and 0, and that will be doing for the relation matrix it is 1, 1, 1, 1, 1, 1, then it was 0.4, 0.4, 0.6, 0.6, 0.4, 0.4, third row was 0, then 0.4, 1, 0.8, 0.3, 0, and all were 0.8 here, 0.8, 0.8, 0.8, 0.8, and this is also 0.8. Okay, and we know how to compute the max mean composition. Right. So just do that. So what will be, suppose b bar dash, if I would like to calculate, so what will be the resultant? It will be 1 by 4, and this will be 4 by 6. So resultant will be 1 cross 6. So it will be means b11, b12, b13, b14, b15 and b16. So to calculate b11, it will be using max min. So it is max and take it the minimum from this. Okay. So multiply this with this. So from multiply this with first column from this. So what is the minimum? 0.5 and 1. It is 0.5. Okay. So now minimum I will not write here. So I'll take it the minimum, and from that we'll select. So 0.51 minimum will be 0.5. 0.5, 0.4 minimum will be 0.4. 0.5 with 1 minimum is 1. 0.5 with 1 minimum is 0.5. 1 with 0.4 minimum is 0.4. 0.3 with 0 minimum is 0, and 0 with 0.8 minimum is 0 again. Okay, and from the select maximum, so it will be 0.5. So b11 will be 0.5. Similarly calculate b12. Let me write here b12. So for that, take it now first row with second column. Okay, so it will be 0.5 with 1 minimum is 0.5. 1 with 0.4 minimum is 0.4, 0.3 with 0.4 is minimum 0.3, 0 with 0.8 minimum is 0, and take it maximum is 0.5. Okay, similarly for b13, take it first row and the third column. So 0.5 with the 1 minimum is 0.5, 1 with 0.6 minimum is 0.6, 0.3 with 1 minimum is 0.3, 0 with 0.8 minimum is 0, from that maximum is 0.6. Okay, so similarly you can write, so b11 will be 0.5, b12 will be again 0.5, b13 will be 0.6, b14 will be again same 0.6, b15 will be 0.5, and b16 also be equal to 0.5. Okay, so this way you can calculate. Fine. one more example we can take it. So suppose I have one set which is suppose low BP, high BP and some stable condition sort of. If I am saying the rule 1 that if BP is low, then a person is not stable. If BP is medium, then person is stable. So for that what I need the low BP, I need the medium BP, and also I need the fuzzy set as stable. Okay. So suppose low BP, let me represent with as W bar. So for that suppose the elements are 0 and its membership is 1, 50 membership is 0.9, then suppose 100 membership is 0.7, 150 membership is 0, 200 membership is 0, and suppose this belongs to universal set X. Then suppose for medium BP M bar, say for this 0 is 0, for example 50 it is say 0.4, for 100 it is say 1, for 150 let me say 0.4, and for 200 suppose it is 0. Again suppose it belongs to universal set X as BP. Then say the stable as suppose represented with S bar, so 0 with 0 plus say 50 with say 0 plus 100 stabilization is 50% plus for example 150 let's say 0.9 plus 200 1 and belongs to universal set Y. Whereas what X and Y are X this is the set which belongs to 0, 50, 100, 150 and 200. Similarly universal set Y is also 0, 50, 100, 150 and 200, something like this. Okay, so if I am making rule 1, so what is that rule? For example, rule 1 says that if low BP, then condition is not stable, so it is not stable. Okay, so for that what can be written? Low BP means it represented by W bar, and it implies that not stable means S bar complement. Okay, so how to obtain the relation matrix here? Area relation matrix will be obtained as W bar coupled with S bar complement, and if not low BP means what? If W bar complement, then what next? Then will be your whole universal set Y. Okay, and then rule 2, if there is a change in antecedent, so then if medium BP, then stable. So I would like to check it out. I would like to compute what is the stability for this if the thing is medium BP. Okay, so how to compute? First obtain the relation matrix R bar, and this will be obtained using this. Okay, and then compute the stabilized condition. So stabilized condition is suppose S bar, which can be obtained using the medium BP, that is M bar composition with your R bar. Okay, so this way generally we can compute the change in the antecedent. Means what is the change or what is the corresponding consequence if there is a change in antecedent. Okay, now let us check it why it is called as approximate. So again let me take the same example as we have already seen, that is R bar. For that relation matrix it was 1 1 1 1 1 1, and it was 0.4 0.4 0.6 0.6 0.4 0.4, then this was 0 0.4 1 0.8 0.3 0, and all were 0.8 0.8 0.8 0.8 0.8 and 0.8. Okay, And what was the a bar? A bar was given as 0, 0.6, 1 and 0.2. Last example which we have seen. Okay, and from that let me calculate b bar dash. Okay, so not b bar dash, b bar. So b bar can be obtained using the composition as a bar composition with r bar, and this can be obtained as 0, 0.6, 1, 0.2 with this relation matrix. Okay, so what it will be? First 0, okay, first let us calculate b11, so which will be max from first row to first column. So what is the first one? 1.4, 0, 0.8. Okay, so minimum will be 0, 0.4, 0 and 0.2, and select maximum from it, which will be 0.4. Similarly for next row, what is next row? It is 1.4, 0.4 and this is also 0.8. I will write b bar here. B bar first element obtained as 0.4. The next is minimum is 0, 0.4, 0.4 and 0.2, and select maximum, so again it will come 0.4. For third row it is 1.6, 1.8. So what will be minimum? This 0, 0.6, 1.2, maximum is 0.6. No, maximum is 1. Okay, maximum is 1. This, yeah, this is not 0.6 but it is 1. From this fourth row it is 1.6, 0.8, 0.8. So 0 is minimum, 0.6 is minimum, 0.8 is minimum, 0.2. So fourth element is 0.8. Similarly for fifth is 1.4, 0.3, 0.8. So minimum is 0, 0.4, 0.3, 0.8. So it will be 0.4. And similarly last also 0, 0.4, 0, 0.2. So similarly it is 0.4. Now let us compare this b bar which we have been obtained using reasoning from this relation matrix r bar. Okay. So according to actual thing, r bar how we have obtained? R bar we have obtained using a bar crossed b bar union a bar complement with y bar. Okay, fine, where a bar and b bar were given. Now from this r bar I would like to complement b bar. I would like to obtain b bar for same a bar. So b bar, actually b bar should be same as of from where the r bar has been computed. So let us compare 0.4, 0.4, 1, 0.8, 0.4, 0.4. Let us go back and let us check it out. What is my b bar here? So this relation matrix which we have been obtained, what is the b bar? B bar here is, see, this is 0, 0.4, 1, 0.8, 0.3, 0, whereas in our case which b bar we have obtained, it was 0.4, 0.4, 1, 0.8, 0.4 and 0.4, 0.8, 0.4 and 0.4, which is not at all equal to this b bar. Okay, that's why this is not exact reasoning, but this is your approximate reasoning. Fine. That is why the name is given approximate reasoning. Whereas in opposite to it, if I will take it the classical logic, there definitely you will get it the same. So again we'll take it the same example where we have taken in the last class, last class, where a was given as 0, 1, 1, 0. I mean last class only we have taken, and R relation matrix obtained is suppose 0, 0, 0, 0, 1, 1. Properly, or let us take this example which we have recently taken For this, let us take this R bar and let us take it A. A is 0 1 1 0, and what will be B? B should be 0 0 1 1 0 0. And what is R? This is all 1, last row all 1, this is 0 1 1 0 0. Okay, let us take it this example and let us check it out, because there also rules same. If A then B. A was this 0 1 1 0 and B was 0 0. B was 0 0 1 1 0 0. Okay, from that we obtain relation matrix as first row was all 1, last row was also all 1, and third row was, second row was 0 0 1 1 0 0. Here also 0 0 1 1 0 0. Okay, and A bar was that. A is that. Now from that let me obtain B using composition. So B can be obtained using A composition with R. So A is 0 1 1 0 and R is this. Okay, so using max min, so let us write first column 1 0 0 1. So from that what will be B? So it will be minimum is 0 0 0 0. So you select what will be max. Max will be from all zeros will be 0. Okay, then what is next row? It is 1 0 0 1. So next will also same. Then next third row is 1 1 1 1. So first select minimum and select maximum from it. So minimum is 0 1 1 0. So maximum is 1. Fourth row is same 1 1 1 1. So again it will be 1. Okay, fifth row is 1 0 0 1. So select this row, this column minimum and from that maximum. So minimum 0 0 0 0. So maximum from all zeros is 0. Similarly next column is 1 0 0 1. So from that also it is 0. So you can see this resultant B which we have been obtained is exactly same as what we have used for the rule which we have defined, and from that this relation matrix has been obtained. So in classical set theory, using this reasoning we'll get it the exact B or exact the thing which we have been obtained for the relation matrix. But in fuzzy logic what will happen, we will not get it the exact thing there. That's why it is called as approximate reasoning. Okay. So this is very helpful for finding out the reasoning and to create or to design the rule. Okay, so with this we stop here. Thank you very much.